So in the previous video, we have understood that we can break down using the Large Hadron Collider and create many fundamental particles that we may discover more in the near future, such as the quarks and also the electrons and the electron neutrinos. We've also looked at the fundamental process. Okay, so in this video, we are going to look at how they come together. Of course, you already have two examples, which is the proton and the neutron. And we're also going to look at this thing called antiparticle. So what is the antiparticle? That's what we should. Okay, so if you have studied the beta plus decay in the previous subtopic, you will notice that there's this thing called a positron or a beta plus particle. Okay, so this beta plus particle is actually an anti-electron. Okay, so then you think to yourself, if the electron has an anti-electron, then the up quark will have an anti-up, and the tau neutrino will have an anti-tau, and every one of these will have antiparticles. You're right. You are right. Okay. But what on earth is an antiparticle? Well, we can think of an antiparticle as, like something that is a mirror image of the other particle. Okay. So the first thing is they will have the same mass, okay, but opposite charge. That's why the anti-electron is positive, but the electron is negative. Okay. And it spins in the opposite direction. So if you do chemistry, you will know through Pauli exclusion principle that particles have a certain spin. But if not, then just accept that the particles just don't sit there, they are actually spinning. Okay, and they're opposites. Right? Not very relevant to our classification, but nice to know. All right. So matter is what we are used to. Particles are what we are used to. Okay. Antiparticles are the mirror image, so they have the same mass, but they have opposite charge. Okay. So for example, if you look at the up quark, the charge of our up quark is positive 2/3 the electronic charge. That means the charge of the anti-up quark will be negative 2/3 the electronic charge. Just like the charge of the electron, this charge is equivalent to negative 1e. So this charge will be positive 1. And so on and so forth. Okay. So you may be thinking for the neutrino, there is no charge. Yes, but they spin in opposite direction. Okay. So if we look at this train of thought, then we understand that, well, if we have a proton, then you can have an anti-proton. All right. And let's say we look at something a bit more exciting, which is your hydrogen. So every single particle or atom that you can find on the periodic table, theoretically speaking, you can make its antiparticle counterpart. Okay, so for example, let's look at the most simple one, which is the proton. So proton and the electron cloud, which is what makes up the hydrogen atom. So let's look at the quarks that proton consists of. Okay, so proton here will have 2 up quarks. I'm just going to write the symbol and 1 down top, making its charge plus 1. All right. And then you have the electron cloud around. Okay. So hopefully you know that the electron doesn't move around the proton like a true train. Okay. It's not a train track. Electron kind of like exists around the proton in a circular cloud. Okay. It's not a spherical cloud. All right. So the anti-hydrogen will consist of the anti-proton. So whatever you have here, you must call it anti-up, anti-up, anti-down. But in symbol format, how do we represent it? We add a bar on top. Okay, so we add a bar, a bar, a bar. All right. So you can see the bars are here in the symbol. Whenever there is a bar, it shows you that it's an antiparticle. So some people may be thinking, Lisa, this electron, why don't have one? Well, this E plus is a special, it's one of the first fundamental particles. So it gets bits, the honorary founding member of the fundamental particles. So this one, there's no bar, but all of it, there is a bar. So let's put it all together inside the new table. Okay, so if you look at this table, the first time it was introduced to you, you only had the matter or the particles, right? but all of it will have an anti. So up will have anti-up. A charge positive two-thirds means we have it. Positive two-thirds E. Then here will be negative two-thirds. Okay, so you can see all of this, we draw a bar on top. All of this anti-particle, you have down, you've got anti-down, strange, anti-strange, bottom, anti-bottom. We are physicists, okay, so you don't have to complicate things. Whatever that's the anti-particle, you just add the word anti in front. Only one person is a little bit special, which is the electron, because, founding member of the fundamental particles. Okay, so, but if you want to call it an anti-electron, go ahead. People know what you're talking about. Just the symbol we use in class more than in Bach. Okay, all right. So it's the same thing. What we did was just we did a mirror image reflection. Okay, so why is antimatter such a fascinating subject for physicists? Well, when particle and antiparticle, like, they go close to each other, and if let's say the speeds are low enough, they will annihilate each other. It means this electron and this positron, if they approach each other slowly and get too close without social distancing, like a Korean romantic drama, they will annihilate each other. Okay, meaning they will cease to exist. Oh, miss, what is this annihilation? They will disappear. Okay, so when a particle meets an antiparticle, it will disappear. And when it disappears, it will release two photons, which is light particles. We will study more about the photons in the okay? So in the back-to-back process, okay? Then the energy is carried away by okay? And actually, it's not like the particle disappears, but the particle converts fully into energy. There is no more mass. There's no more particle. Very interesting thought. And of course, we have seen this replicated in the lab before, inside the Large Hadron Collider. Okay, so the process of annihilation will happen whenever a particle meets an antiparticle. All right. But for you right now, what you need to know is just how we classify them and the names. So it's more like, hi, these are what makes up the fundamental particles. Okay. All right, let's move on. So, classify matters, okay? Generally, we split them into two, which is hadrons and leptons. So you think to yourself, leptons sounds very familiar. Well, if you pay attention, everything that is in this green portion are called leptons. But the reason, something I want to point out to you about this L is that lepton stands for the light ones, not heavy. So this L here is for light particles, not light the electromagnetic radiation, but light as in low mass. Okay, and hadrons are made out of quartz. So everything that is heavier or have a large mass, everything that is heavier here, this one are what we can call hadrons. So whenever you see the ons, it's for particles. So it's ons, those are particles. So ons, right? And this H stands for wind. I find that easier to recall. So hadrons will consist of quarks. So hadrons consist of quarks. Different combination of quarks. Okay? So that's why when we classify metals, we can have hadrons, we can have leptons. Okay? And within the hadron classification, you can split it into baryons and mesons. Okay, so what differentiates them would be baryon will have 3 quarks and mesons will have 1 quark and 1 anti-quark. So immediately you should think to yourself, well, an example of a baryon would be our good old proton, right? Because proton consists of 1 up, 2 up, 1 down quark. So the second one will be neutron, because neutrons consist of 1 up, 1 down, 1 down. Then you could ask yourself, hey, you think that we could also have a combination of other type of up and down? Any three of these 12 particles. Only 3 of these 6 particles will give you a hadron. But there's a caveat here. This top, bottom, and charm strings are not very stable. Okay, they are not very stable, and with time, they will decay into up quarks and down quarks. All right. So these are the options. Could there be other particles? Sure, but this is a popular one. All right. So mesons, the list is endless. Okay. It's like choose your own anti-particle thing. You can take some from here, take one from here, and take one from the anti-particle and make your own. Okay. So this one, we can have many examples. I'm just going to give you a few. Example of meson would be something that we can call a pion. Pion. Symbol that we will use is pi plus. Okay. So this consists of an up quark and an anti-down quark. Okay, so there are a lot of other particles, other combinations. Okay, maybe just to fill up the table, I'll give you another one. I'm just copying stuff like this from Wikipedia. Okay, you don't need to know. What you need to know is actually to find the charges of this. Okay, so another one that it's pretty straightforward is like on. Actually, I don't know what's the story behind these names, but this will be K plus. Okay, so this consists of a up quark and an anti-string quark. Okay, so if you're wondering, there are so many ones. If you go up to Wikipedia, it's a long list, or any kind of scientific website, there's a long list of disciplines. So I think just to create some form of familiarity, I will introduce another variant to it. This is sigma. Okay, so symbol is sigma plus. We'll see why there's a plus there pretty soon. This will be upstream. Okay, so this one is not very common because eventually the strange will decay into the down and then drive it up. Okay, let's think a bit about the charges. Okay, so what is the charge of a pion? You have the up quark. The up quark has a charge of positive 2/3, and the down quark has a charge of negative 1/3. But it's anti-down. So because it's anti-down, you will then have to make this positive. Okay, so I'll write this for you. This positive here is due to this empty particle. That's why the charge for this will be 1. Okay, and the same thing happens for kaon. Okay, so what you actually need to know, important. Okay, you need to remember or memorize proton and neutrons. That's it. But another skill you need to know is to find the charge of the particle based on charge based on the fundamental particles combination. Like what I did for my pion plus. That's why it's called pion plus. So as an exercise, you can do it for sigma and kaon, and you will see that their charges are all 1 plus. Okay, for the fundamental particle combination, whether it's particle or anti-particle. All right, so this is what you need to do. Not so much to memorize the composition. Normally, they will give you the composition and ask you to reduce the charge. You do partial questions, or they can give you the charge and ask you what is the other part. All right, so this is the classification. So let's go through it again. Matter, hadron, and electrons. Okay, so the actual definition of hadron is what? Don't directly particles. Hadrons here, they are affected by the strong nuclear force. So the previous video, we have already covered what hadrons are. I mean, what strong nuclear force is, which is due to the interaction of gluon. So this gluon You see my gluon up here. This gluon will glue the up, down, the up, down together. Right, as mentioned by different. It's a force carrier. So leptons will be not affected by strong nuclear force. Because this is electron, so it's the electrons of the force. Okay, so not affected by strong nuclear force. In case an off chance they ask you to compare and contrast hadron and lepton, this is the main comparison. All right. So, and for leptons, it's pretty straightforward. We're talking about all these green particles from electron to electron neutrino, muon, muon neutrino, tau, tau neutrino, and so forth. Okay. But for hadrons, we can further classify them into baryons. So what are baryons? Baryons have 3 quarks. And meson, what are meson? Meson will have 1 quark and 1 anti-quark. Okay, and how do we put them together? Gluon, strong nuclear force. Okay, so what you need to know here, besides proton and neutrons composition, is to either deduce the charge based on whatever combination of fundamental particle they chose from the table, or given the charge, decide what the other fundamental particle is. So personally, the way I remember the ones on top here, top will be up, charm top. It's charming to be up and be on top. So all of these will have positive 2/3. The anti will be negative 2/3. So whatever that is opposite of all this will be negative 1/3. Down is strange. It's strange to be down and in the bottom. Okay, formula. All right, so it's negative 1/3 E. Okay, and if it's empty, then it's positive 1/3. Right, so I think of it in rows. That's how I memorize this. Okay, so if you're wondering, if we can classify matter, can we also classify antimatter? Of course. So I'm just going to paste this thing here. And then I will add the word anti in front of all of our little things here. So this matter can be called an antimatter. And then this hadron can be anti-hadron, can be anti-lepton. And because of this, you will have an anti-baryon and an anti-meson. Okay, but will it consist of 3 quarks? No, it will consist of 3 anti-quarks. But this one is 1 quark, 1 anti-quark. The quark will become anti-quark. The anti-quark will become a quark. So this one can stay, right? So everything else, you just add anti. Then you're thinking to yourself, what's the example? Is there such thing as an anti-proton? Of course. Or it's an anti-proton. What symbol do we use? Normally, proton will put P, so put bar P. Just like the symbol for proton here. Not like this one. Okay. So if you think about the mirror reflection, so you can see both sides as well. Look at the mirror reflection. If proton is up, up, down, anti-proton now will be anti-up, anti-up, anti-down. Okay. And number 2, you will obviously have an anti-neutron, anti-neutron. This will be bar N. N. So this will be anti-up, anti-down, anti. And if you calculate the charge, right, this charge will be, let's calculate it just for that. What is the charge of anti-up, anti-up, anti-down? Well, you can find the charge now. This charge will be anti-up is, look, up is 2/3. So anti-up will be negative 2/3. Okay, negative 2/3 plus negative 2/3 plus positive 1/3. So this one will be negative 1/3. Okay, so that's how we can see that the antiproton will have the opposite charge to a proton. But the anti-neutron will it still be negative? Oh, So to find the charge of the antineutron, you will take negative 2/3 E plus positive 1/3 E plus positive 1/3 E. And this one, negative 0 E. So neutral is still neutral. But what makes up the quarks inside is now all anti-quark. Okay? So if you follow along this train of thought and you look at mesons. So for mesons, the first one I gave you is pion, right? So now we will call this anti-pion. Okay? So if you think about the sign of anti-pion, that will be pi minus. Okay? So instead of instead of a up, it will be anti-up. Instead of down, anti-down, it will be down. And now your charge for this one will be equal to anti-down is negative 2/3 E. Down is negative 1/3 E. So you get negative 1 E. So you see the charge has reversed between pion pi plus and anti-pion pi minus. We add the word anti-down. And also the same thing will happen for our kaon. So we're just going to call this K minus, right? And then this will consist of up and this. And if you want to find the charge, same thing will happen. So I will not repeat again. So again, the same idea. You must be able to find charge based on the fundamental particle combination that is at hand. Not so much as to memorize this, besides proton and neutron. Because that one is the most basic one you expected to. So this is how we classify particles. Okay. So in this video, we understood that the fundamental particles have a mirror particle, which is what we call the antimatter or antiparticle, which has the same mass but opposite charge and spins in the opposite direction. To represent the antiparticle, we will add a bar on top, except electron, because electron is special, founding number, the fundamental particle. Okay, so for every particle, there's an antiparticle. For example, for hydrogen, there's an anti-hydrogen. And for example, the proton here will be up, up, down. So the anti-proton will be anti-up, anti-up, anti-down. If there's an electron cloud, here there will be a positron cloud. Okay, and these are just theoretical. We produce this inside the Large Hadron Collider. Okay, but what happens when a particle meets an antiparticle? It will annihilate each other. It will disappear and become pure energy. How cool is that? All right. And of course, since we can put them together, particles or antiparticles, we can also classify them matter and antimatter. Okay. So the main classification branch would be hadron. Hadron consists of baryons and mesons. Baryons are things that have 3 quarks. Mesons are things that have 1 quark and 1 antiquark. Leptons are electrons and neutrons. These are the electrons. And then the electrons and the electron neutrinos. Okay. So the way to differentiate hadron and lepton, the actual classification criteria is hadron is affected by strong nuclear force, whereas lepton is not affected by strong nuclear force. Okay, so the mirror image of matter will be antimatter. So for antimatter, we will have antihadron, antilepton, antibaryon, antimeson. And from here, you can see that whatever it is that we did on the left side, we are repeating on the right side, but we are putting anti in front of all the naming, putting a bar in front of all the symbols, and adding a negative sign in front of all the charges. So the charge, what we really need to know in past year questions or for you right now at this level is not so much to understand how they come together, but just to know and to find the charges based on whatever fundamental particle combination. All right, so that is it for classification. I will see you in the next video. or something else. Bye bye.